All right, hello everyone. We are taking a look at day 3 on section 5, and we're talking about solving more inequalities. We're talking about solving rational inequalities. So because these are inequalities, we're still using the same method that we saw in the previous day of notes. So let me just take you back there real quick. When we were solving polynomials, we were looking for critical values, and then we were testing the intervals, right? So as an example, we would take the polynomial, solve it, finding those critical values, divide up the number line into those intervals, and then pick those test values to see what the results were. All right, we're doing the same thing here as well, except there are a couple extra steps because in this case we are not using a polynomial, we're using what we call a rational function, and that means we have fractions involved. So the first thing we have to do is to make sure that we have a single fraction. And so let's take a moment and review how to do that. We're going to create a single fraction by making sure that we have a common denominator. So in part A, if I have 2 over x plus 3 over 1, well then we're going to multiply that 3 over 1 by x over x so we can create a common denominator of x. So that gives us 2 over x plus 3x over x. And now with a common denominator, we can now combine the numerators over a common denominator. If they were like terms, we would combine them, but they're not like terms, so they just sit as is. Notice we have a single fraction. So that's a rational function. Here we have 4 over 1. So I would multiply that 4 over 1 by the other denominator of x minus 3. Now you have to be careful here because when we're looking at distributing the 4, you want to combine the negative sign with the 4 when you do that distribution. So that means in the numerator we have an x, we have a positive 5, and then we have a negative 4 times x and a negative 4 times negative 3, so positive 12 there. We have a common denominator of x minus 3. And then we'll combine our like terms in the numerator. So x minus 4x is negative 3x, and 5 plus 12 gives us 17 over that common denominator. Here in our third example, you can see that we have 2 fractions and they each have a different denominator. So we're going to multiply each fraction by a multiplier of the other denominator. So in the first fraction, we want to have here a denominator that also includes the x plus 3, so we're multiplying top and bottom by x plus 3. And we're multiplying the second fraction, top and bottom, by the other denominator of x minus 3. So we're going to distribute the 5, we'll distribute the positive 3 to create our numerator. So in the numerator we have 5 times x, 5 times 3 times x, and 3 times negative 3. And in the denominator we have a factor of x plus 3 and a factor of x minus 3. Notice we're not multiplying them together, we're going to keep those factors side by side. Combine our like terms and we get 8x plus 6 over that common denominator. So that will be the very first step we will see in these problems today. We need to create a single fraction, then we can find the critical values. And that's summarized down here. So the critical values are going to come from 2 places, from the numerator and from the denominator. For the numerator, we're going to set that numerator equal to 0 and solve for x. And what this is really doing is this number is not a random number, but it's representing the x-intercept of that graph. And then we'll have to pick the right brackets to use depending on the inequality symbol that we have. Now the denominator is also going to provide a critical value. You want to set the denominator equal to 0. I think you might have a typo in your notes. I think that was an older version and I had adjusted it recently. Yours might have said set the numerator equal to 0. Fix that. We are talking about the denominator here. So we're going to set the denominator equal to 0 and solve for x. And this is also giving you a critical value. The number, again, is not a random number, but it is telling you something about the graph. And because it comes from the denominator, what you're really doing is finding the domain restriction. And it's represented by a vertical asymptote on the graph. And because there's a vertical asymptote, that means there is no graph right there. So if there is no graph, that is a natural division It is a natural boundary between intervals on your number line. Just to draw a quick illustration, a rational function often has these two separate branches. So let's pretend we have a vertical asymptote. There are often horizontal asymptotes, but we're not really worried about those so much right now. And let's say, for example, these are the two branches. And if we were to ask, just by looking at the picture, what are the critical values? Well, what we're doing here is we're taking a look at the x-intercept. That would be a critical value that would divide the intervals between those parts of the graph that are above the x-axis and those parts that are below the x-axis. And then even this vertical asymptote is also dividing the graph between those that are below the x-axis and those parts of the graph that are above the x-axis. So you can see that we're going to have several different critical values that come from different places. And because they come from different places of the graph, that means that we have only certain kinds of options available for the brackets. So when we're talking about the denominator, we can only use the rounded brackets because that means we can go right up to that value, but we can't actually equal that value, because if we're trying to equal that value, we would be at the vertical asymptote, and there is no part of the graph right there. But then the numerator is representing the x-intercept. So we can go right up to that value if we have the greater than or equal to sign or that less than or equal to sign. And we'll use those square brackets to represent those. So that's the overview. Let's go through and take a look at a couple examples to walk ourselves through the entire process from start to finish. Okay, so I'm going to flip over to the next side, and we're looking at, this is page 25 in our note pack. And I'm going to start over here with example number 2. So in example number 2, this is really built off of a similar type problem that we're just looking at in the previous section, where we were practicing how to combine those fractions into a single fraction. So let me give myself a little bit more space. I'm going to rewrite this problem, because right here I want to set up my multiplier, and I'm going to multiply top and bottom by that x plus 3. And then remember to include that negative with the 4 when we do that distribution. So in the numerator we have an x, we have a positive 5. Negative 4 times x and negative 4 times 3 will give me a negative 12. And then in my denominator, I now have that common denominator of x plus 3. So all of that is less than or equal to 0. Let's go one step farther and combine our like terms. So we have a negative 3x minus 7 over x plus 3. All right, so this is what we're going to be testing when we set up those intervals. So we're going to be using this to find the critical values, to find the intervals, and we're going to ask ourselves, where does the graph exist underneath the x-axis, less than 0? All right, so step 1, let's find those critical values. Now they come from two places. We have to check the numerator, and we also have to check the denominator. And so I'm just setting up two columns here for each of those little calculations. So for the numerator, we'll take the numerator, and we will set it equal to 0, and then we're going to solve for x. So in this case, we end up with a funny fraction, and it will help us if we can turn it into a decimal value temporarily, just so that we can figure out what test value that we want to pick when we get to the second stage. So we'll just say about negative 2.3. For the denominator, we're taking that x plus 3, and we're setting it equal to 0. And when we're solving, this is telling us the other critical value. Now remember, this is actually the domain restriction. We're not allowed to use negative 3 as a solution. And so when we're talking about a domain restriction, we usually say this cannot equal 0, so this cannot equal negative 3. But the point is, this is a critical value. And because it comes from the denominator, we're going to use those rounded brackets when we set up our interval. So I do this just as a mental reminder that I need rounded brackets on my negative 3. But for my numerator, what kind of brackets are we going to use? I have to check the inequality sign, and this is a less than or equal to. And because of that or equal to part, we're going to use square brackets. So again, I'm just using this as a way to remind myself to include square brackets whenever I use that number. So here's my number line. Organizing our information from smallest to biggest. -3 is the smaller number. -2.3 is the bigger of those two. Again, that's the decimal value just so I can figure out what test values to pick in between each interval. This number is really -7/3. So now that I set up my intervals, I'm going to make my table. So here's my column for intervals, my test value, let's see, my calculation, and then my results. So my intervals are going to go from -∞ to -3. Again, a rounded bracket around the -3. And then from -3 to -7/3. Again, square bracket around the -7/3. And then my third interval is from -7/3 up to +∞. All right. So I need to pick a test value, some number that's between -∞ and -3. So how about -4? For this middle interval, I have to pick a value between -3 and -2.3. So how about -2.5? And then for the third interval, I need to pick a test value, anything between -2.3 and +∞. And I'm going to pick 0 because, of course, it's easiest to do our calculations with 0. So we're going to take each of these test values and plug them back into this inequality right here. So let's see if I can fit this on the screen. So for example, we will have a -3 times the input of -4 minus 7, all divided by, here's my input of -4 plus 3. Now, if you do enter that into your calculator, be very careful. Make sure that you surround all of the values in the numerator with parentheses, surround all the values in your denominator with parentheses, so that you are separating that division bar with parentheses from the top and the bottom. We will get a result of -5. Here I'm going to plug in my input of -2.5, so it looks like -3 times my input of -2.5 minus 7, all divided by, here's my input of -2.5 and plus 3. I'll get a result of +1. And lastly, for 0, here's -3 times my input of 0 minus 7, all divided by my input of 0 plus 3. So that one simplifies to -7/3. So then when we are looking at the results, again, you're always asking the question, are these positive or negative? Are they less than 0? That's what we want. So the ones that are less than 0 are the first and the third result. That means the first and the third interval will be our solution interval. All right, so we have -∞ to -3 in union with square bracket around the -7/3 up to +∞. Again, that U stands for union. It's both of these together that are the answer. So I want to walk you through the steps one more time, looking at one more example, and so we'll slide the paper over to the left and look at example number 3. This one is what we're going to finish up with here. Again, we want a single fraction, and technically we have 2, so we want to move everything to the same side. So let me start by subtracting 3 from both sides, so that we have 0 on the other side. But of course we don't have a common denominator, and that's what we need. So let's multiply top and bottom by the other denominator. And don't forget, we want to include that negative with the 3 when we distribute to the binomial. So our numerator is a 2x minus 7, and a -3 times x, and a -3 times a -5, so +15 there, over that common denominator of x, minus 5. Let's combine the like terms, so 2x minus 3x, and -7 plus 15 over that common denominator. Okay, so this is the inequality that we're going to test. We have a single fraction on one side, 0 on the other. So step 1, we need to find those critical values. Remember, some come from the numerator and some come from the denominator. So my numerator is negative x plus 8. We're going to set that equal to 0, and it'll be a little bit faster solving for x if we just move the negative x to the other side. So that is one of my critical values, positive 8. And then for the denominator, x minus 5 means that my other critical value is 5. Remember, technically this is a domain restriction, so technically x cannot be 5. That's where the vertical asymptote is going to be located. And as it comes from the denominator, I will have no graph existing at 5. So we use the rounded brackets, meaning our graph will go up really close to 5, but it won't actually equal 5. And then for the numerator, we have to check whether it's rounded or square brackets, and my inequality symbol is less than or equal to. It's the or equal to part we're looking for, and that would suggest we want square brackets. Okay, so now let me do my second part. So here's my table, here's the interval, here's my test value, my calculation, and the result. All right. So, you know what? I want to draw that number line so I can see a diagram of what we have. We want to organize our information from smallest to biggest. So, from negative infinity, we then come to 5, then to 8, and to positive infinity. So, my first interval is going to be from negative infinity up to 5. 5 as the rounded bracket. Then we have the interval from 5 to 8. 8 has the square bracket. And the third interval, 8 to infinity, again square bracket on the 8. So for a test value, let me pick a value of x that is somewhere in this range, and so why not use 0? Then we need to pick a value that is somewhere in this range. How about 6? And then I need to pick a test value that is somewhere in this range. How about 9? So we're going to take each of these and plug them back into our rational inequality. So I've got a negative input of 0 plus 8, all divided by input of 0 minus 5. So that gives me a result of 8 over negative 5. It's a negative fraction, in other words. All right, now with an input of 6, I will have a negative 6 plus 8 over an input of 6 minus 5. So that will give me positive 2 over positive 1. And then lastly, input of 9, so we will have a negative 9 plus 8 over input of 9 minus 5. Okay, so that will simplify to a negative 1 over 4. Again, all we really want to know is the answer negative or positive, right? Because we're really just looking at the sign. Because we're looking for the result that will be less than 0. So that means we want negative results only in this example. So that will be the first and third result, which means we want the first and third interval for my solution. So my solution is going to be negative infinity up to, but not including 5, in union with 8 up to infinity. And that is our final solution.